Now let's look carefully at the graph we've obtained underneath. This is what's called a model complexity graph. Notice that on the left, we have a model that underfits and gives us high training and testing errors. The model on the right overfits and it gives us a very low training error, but a high testing error. The model in the middle is just right and it gives us relatively low training and testing errors. This is the model we should pick. So here we have a bit of a clearer picture. In the x-axis, we have the complexity of the model. So we go from linear, degree 1, all the way to a polynomial of degree 4. On the left, the models show underfitting, or high bias error. On the right, we see overfitting, or high variance error. And in the middle, around the value 2, there is a happy point, where we are neither underfitting nor overfitting. Thus, we decide that the best model for our data is a polynomial of degree 2. So far so good, right? Oh, what's happening? What is this? Oh no, what did we do? We broke the golden rule. Never use your testing data for training. We've made a huge mistake. But let's see, what did we do here? Here's the problem. We used our testing data to train our model. We're not supposed to use our testing data until the very end, and we used it to make a huge decision about our model. This is completely forbidden. You're not allowed to touch your testing data. So how do we fix this? How do we make a good decision about our model without using the testing data? Well, no need to panic. We can fix this by breaking our data set even more. Now, instead of having a training and a testing set, we'll add a cross-validation set. Now, the training set will be used for training the parameters. The cross-validation set will be used for making decisions about the model, such as the degree of the polynomial. And the testing set will be used for the final testing of the model. Now our graph looks so much nicer with a cross-validation error instead of a testing error. So let's recap. Here we have the model complexity graph and the example all together. On the left, we see underfitting, or an oversimplification of the problem. This is bad on both the training and the cross-validation set, because our model simply does not capture the complexity of our data. On the right, we see overfitting, or an overcomplication of the problem. This is great on the training set because we're memorizing it, but bad on the cross-validation set because the model does not generalize well. And in the middle, we have the perfect model, which is good on both the training and the testing set. I like to imagine underfitting as coming to an exam unprepared. No matter how hard you try, you won't do well. Overfitting is like studying for an exam, but instead of trying to understand the material, you just memorize the book word by word. You can repeat anything that is given, but you won't be able to answer new questions about the data. A good model is like studying for an exam and coming ready to answer any questions on the material. And here's just a general picture of the model complexity graph. Of course, they may not look as pretty, but in real life you see that most of the time your models will exhibit a behavior like this one, whereas the model gets more complex, the training error gets smaller and smaller, and the testing error starts big, then decreases, and then increases again. On the left, you underfit. On the right, you overfit. And the perfect point is here, where the graphs just start the distance from each other.